rigorous approximation of invariant measure beyond the
Thank you. Let me thank the organizer for this occasion to talk, and it's always a pleasure to be here. So, what I will talk about is rigorous computation of invariant measure. Rigorous in the sense that we will produce some representation of interesting invariant measure up to given explicit bound on the error we are making. Of course, this is in some sense one of the first steps which are important to do to a more ambitious project, which is to let the computer help us to understand the statistical property of the dynamics, like answering to questions like, is this system mixing? What is the speed of mixing? What is the entropy? Maybe have an estimation like the entropy is between this number and this number, or what is the dimension of this attractor, or what is the variance, as I learned a few minutes ago, of some observable. Even linear response can be related to this. So, but the first thing is, well, an important thing to go to answer all these questions is to understand precisely the properties of the invariant measure we want to consider in our system. So, in this talk, I will talk about computing this invariant measure up to given error. But what means to compute an invariant measure, or to compute a measure in general? A measure is not a number, it's something much more complex. The idea is, the trivial idea is that you consider a space of measure where you are interested in, you put a distance on it, and here you have a big choice, and the choice will be important for the following. For example, a distance which can be defined for any pair of probability measure is the Wasserstein distance. This is, well, a way to define this distance is the following. You take the two measures, you take all the observable with Lipschitz constant less than 1. You test the two measures on these regular observables. Then you take the supremum, and this gives you a distance between the measures, which can be applied to any distance, any pair of measure, even if they are not, I mean, they are not regular, like absolutely continuous, and so on and so on. This is, I have to say, this is related to the work that is not explicit in this definition, but let me just say that this is related to the work which is needed to transport one measure into the other. So there are equivalent definitions that are more explicit on this point of view, but let me just give this and say this is a distance we will consider, and this is the Wasserstein-Kantorowicz distance. If the measures are regular enough, you can also consider some other distance, like the L1 distance or L infinite, or even other distance. Now, rigorously approximating the measure means to up to small error in the distance that you have choose, means to have an algorithm such that you can certify that you give to the computer the error you want. It makes a lot of computation, then it gives you a representation of your measure, like, for example, a combination of delta, or like an absolutely continuous invariant measure which is regular enough, such that the distance and the error you are making is less than the given error. And of course, since we want to use this result like a tool to produce rigorous statement, like tool to produce computer-aided proof, we want not only to say it's possible to design an algorithm to do the job, but we want really to implement it and make it run to the end, because this is a big difference. Sometimes it's not easy to find algorithms that can arrive to the end of the computation in non-trivial example. So we want to implement and try and to see the result. So in some sense, this work is made from two parts. One is to understand how it's possible to do it, and then implementing and seeing the result at the end. So if we want to compute the invariant measure, how we can do it? The main tool that is used in many questions related to the statistical property of the dynamics is the transfer operator. I suppose here everybody more or less knows what is the transfer operator, but let me just say that once you have, let's say, let us consider a metric space and a map from the metric space to itself. Let us consider again the space of probability measure on the space where the dynamics is, and the dynamics on the space induces a dynamics even in the space of the probability measure, because as the map moves the point, it can also move measure by this formal definition, which is general enough to consider this measure. This is called the transfer operator. Why operator? Because if we extend the space of probability measure to a vector space by considering any measure and then measure with signs or complex valued measure, this operator is linear, and this is a main property, as we will see. But first, let me say that now invariant measures are fixed point of this operator. So at the end, we want to compute with a certified error fixed point of a certain linear operator. Of course, here we are starting with a very big space of all the measure with sign. Sometimes it's much more comfortable to restrict the action of the operator to more regular measures, so maybe you can find more easily, of course you can find less fixed points, and maybe you can find the fixed point you are interested in, because of course there are, given a map, there can be many invariant measures, but maybe you are interested only on the most regular one. So an important step is to choose the right functional space where to start your work. Anyhow, let me say that if you approach the problem from the abstract point of view of saying I want to prove that there is an algorithm doing this job, or maybe disprove it, there are general results saying that in very general, under very general assumption, if you have an isolated fixed point of an operator, then this fixed point can be computed up to any given error. So you can be led to conjecture that maybe there is a general statement like this. If a dynamical system is in some sense computable, then the physical measure is computable. If there is a physical measure, then the physical measure is computable. Or if the system is computable, then there must be some interesting computable invariant measure inside or somewhere. I tried to prove this until I found the counterexample. There is a computable, now I will not give here the general definition of what is a computable map between metric space, but it's something quite natural. There is a whole branch of, there are many people working on this. This is called computable analysis. There are books and so on, where they define what are computable maps within metric space. They search what is computable, what is not computable. And what we discovered is that it's possible to find an example of a computable dynamical system, which is a continuous map on the circle, for which there are no computable invariant measure. There are many invariant measures, but among this big set of invariant measures, there is no a computable one, in the sense that computable up to small error in the Wasserstein distance, which is a weak distance. So these measures are really badly non-computable. Now, I will not define exactly the meaning of this counterexample, and will not give the counterexample, but I just say this to warn that there are some theoretical computer scientific difficulty hidden in the problem in some sense. There is some theoretical scientific sophistication in this kind of problem if you approach it generally. I have to say that this example is, of course, a little bit pathological. It involves the use of numbers which are not computable, but they are semi-computable, and so on and so on. This is something that is more related to, indeed, theoretical computer science, and so on and so on. And this example, you will never find it in real life, in real models of dynamical systems. So let us forget this, and now let's go to real dynamical system that you can find in everyday life, and real computation, really feasible algorithms. So we said we have the transfer operator. We want to compute fixed point of this transfer operator. Of course, you will consider the transfer operator acting on an infinite dimensional space. The first idea you can have, and this is probably the most effective one up to now, is to find a finite dimensional approximation of the original transfer operator. Then this can be seen as a matrix. You compute the fixed point of this, and then you extract from this the information, some information on the real fixed point. Of course, to use this, you need a kind of stability theorem for fixed point, saying that if L delta is a good approximation in some sense of L, then the fixed point of L that you are trying to compute are near enough to the one you can directly compute with your computer. Of course, there are several stability results, and even some of them have been used in the literature to make this job, to compute invariant measure. For example, the famous stability result by Keller and Liverani. We started trying to apply these, but we found that it was, for us, not so satisfying, because the result is very strong, but it also needs strong assumption, like that Alazota-York inequality is satisfied for both the system. And it also involves the computation of something which is not very easy to really implement. And so we tried to find a kind of simplified statement which gives a weaker result, but which needs weaker assumption and asks for weaker, simpler computation. So this is a kind of minimal result that we found useful for the job. And the result is like this. So now consider a sub-vector space of the space of measure with sign on your phase space, and consider the transfer operator acting from this space to itself. So, for example, we can, for example, we can to go to something that can be easily understood. This can be the space of measure which are absolutely continuous. So you take this and you take the L1 distance. But the result is more general. But to understand, think about this as this is L1. So suppose that F and F delta are in your space, and they are the real fixed point and the fixed point of the approximated operator. We want to estimate the distance between F and F delta. Now consider the space of the measure in your Banach space which have 0 average. This will be important to consider because, you know, this space is important when you consider like decay of correlation. If the system is mixing, all the measure here will be sent to 0 if you wait enough time. And we will see how we will use this. Now, suppose that if you apply the approximated operator to the real fixed point and the real operator to the real fixed point, which is the identity here, then the distance that you have is smaller than a certain number you can estimate in some way. This is a way to say that L delta is an approximation of L in some sense. Of course, here one can ask, how can you have this estimation if you don't know F? Here you will have to make something to have this estimation a priori. For example, because you know some property of F and some property of the operators, and you do this estimation a priori. And this will be the part that in our approach will be made with a kind of a priori estimation. Then there is another estimation. Suppose that you find some n such that for each measure in your space, suppose for each absolutely continuous measure with average 0, the approximated operator applied n time to this vector will contract it better than 1/2. Then we will have a bound. Let me explain how this is useful. Because here, how you can find this n? Because here you apply the approximated operator. So this estimation will be done by the computer. In some sense, the computer will only, for example, if you take this will be a finite dimensional approximation of your operator. So you can iterate it several times until he contracts the space of 0 average vectors. And so let me just say this is something that is okay because it's like a finite dimensional estimation for the decay of correlation of the system, which can be made by the computer. So you have not to think about what is the decay of correlation of your system and so on and so on. But this will be checked by the computer, and this is a good thing when you want to implement. Then, suppose, consider this coefficient Ci, which are the norms of the approximated operator, again, restricted on the space of 0 average measure. This is, these are assumptions to be verified. This is the definition of what is Ci. Then, if everything is as above, the distance between the real fixed point and the one you can find with your computer is less than 2 times this number times the sum of all the coefficients. And this is a sum with n summand, where n is this one. So if n is not too big and epsilon is small, the error you will make will be maybe small enough for your purposes. Okay, let me precise a little bit better how you can do this estimation. I have to say, this is a simple statement, and with a simple proof. This is not really a big theorem, but it is what we needed to really apply to really compute the invariant measure feasibly. So let me precise here. I said we can do this estimation in some way with some information on f. A way is the following. For example, suppose that you know some information on f, like, for example, a bound on the BV norm of f, which, as probably many of you already know, is trivial once you have the Lazota-York inequality. And suppose you can bound this norm, the norm of the difference of the two operators, considered as an operator from BV to L1. This is not very difficult because it's an operator from a regular space to a less regular space. So in some sense, from how you define the approximation of L, you can maybe write something and you have only to apply this difference on function which are fixed BV norm. So they are regular, you apply this difference on regular function. So probably it's not too difficult to find an estimation like that. So you can bound the strange L1 norm with a product of things which are easy to obtain. And so this estimation can be done in this way. In other cases where you have not BV and N1, here you can do other things. I will just mention very briefly, but other things, but using the same idea. So let me go faster because see, I'm going very slow. So let us give an example of application of this theorem in a very simple case, which was more or less already known with different tools, but this is the simplest case, the piecewise expanding maps. So what we do for piecewise expanding map? We choose an approximated operator, which is the simplest one you can think of. You replace your system with a Markov chain, which is defined in this way. This is called the Ulam discretization of your system. It's very easy. You have your space, you divide your space into cells, then you compute which is the portion of these cells, the cell 1, which goes in the cell 3, which is the portion, and this will be a transition probability, and you make a Markov chain with this. This is a finite dimensional system. You can compute everything on the Markov chain. You apply the fixed point stability theorem, and then you find the distance from what you have computed and what you wanted to compute. So let's give some little bit more detail. So let's suppose we want to apply this on a very simple class of system when we know many things, the piecewise expanding maps. These are maps on the interval, which have maybe they have many branches, but each branch is regular enough and expanding. It's well known that these maps, the transfer operator associated to this map is regularizing in some sense if you consider the BV norm and the L1 norm. In which sense? The sense is that if you take a starting density and you iterate by the transfer operator, the variation of the iterate is bounded by this quantity, which is a function of the initial variation multiplied by a number which is smaller than 1. So the variation will be reduced at this step, plus a constant which depends on the regularity of the system. And both this constant can be explicitly estimated once you have the formulas for the map. So this number can be supposed as in this definition, and the other coefficient can be bounded by this quantity, which contains many things, but all of these things that you can find it by knowing the formula of your map. So what is the use of this inequality is that, as you can figure, if you iterate many times this inequality, since 2 lambda we suppose is smaller than 1, this gives you a bound on the variation of the iterate of any regular density, and at the end it gives you a bound on the variation of the physical invariant measure that you want to compute, which will have a bounded variation density. So the idea is the one I was telling before, only I have to say that you have to estimate this. This can be again estimated starting from the coefficient of the Lasota-York inequality and the size of the partition. Delta is the size of the partition that you choose to make the Markov chain. And well, this also is easy, but I don't want to enter into detail. This is also an easy estimation. And you do, as I was saying before, and you obtain an estimation for this. So the algorithm will be the following. You compute the matrix associated to the Markov chain that you want to use. Of course, if you want everything rigorous, you have to take in account also the small error you can make in computing this. So you have to implement a certified computation of things like this interval is sent here, and then you intersect with the other set of the partition, and you want to know what are these measures, and you want to bound it in a certified way. So it takes some time, it takes some small mathematics to do, and some idea to make it fast, because you will need many small pieces. And then what you do is to compute the famous n such that your Markov chain contracts the space of zero average vectors. And then by this, you extract the error, which is the same I was telling before. The difference between this formula and the one which is in the theorem is that you have to take also, you have to consider also the small numerical error which is made in the computation of the fixed point of the Markov chain, and many other, and this kind of things. Anyhow, the idea is that one. The first question is this algorithm able to produce a computation of the measure up to any small invariant, up to any small given error? Because the theorem I showed is like a posteriori estimation. You start, you decide the size of a partition, you start, then the computer iterate the discretized system. If the n is small enough, your error will be small, but you don't know a priori if you will need many iterations to contract this zero average space. In some sense, you don't know a priori if the system is fastly mixing at a discrete level or not. But the computer will tell you. So it can be possible, and indeed it can happen, that you choose a very small partition, then you start the computation, then you obtain a huge n for which your error is not small enough, small as you wanted. But you can also try to prove in a certain class of example that this algorithm will work and it will give you an error which is small as you want. Let me just say, in the piecewise expanding map, you can give an estimation for the size of n, which will be of the order of the logarithm of the inverse of the size of the partition. So since the error is like n times, this is proportional to delta, because we have seen before. I don't know if, let me just, this estimation is proportional to delta, the constant times delta. So at the end, if n is like logarithm of the inverse of delta, then you have like logarithm time delta, and it will go to 0. So for piecewise expanding maps, the algorithm can work up to any precision, but this must be proved. Sorry? Sorry. B, where is B here? But anyhow, B is the second coefficient of the Lazota-York inequality. But the notation is that B prime, okay, this is B prime.
But for example, the Gauss map
Sorry, this, well, here in the picture I put more example, but here in this estimation I'm considering, I'm considering piecewise expanding map with a finite number of branch and finite derivative. For infinite number of branches is more complicated, and even if you have infinite derivative, it's more complicated, but still you can do something. Indeed, in the example I will give now, we consider, okay, this is, let me just say something that I already said. Here, you have to certify everything. So you need some library that do the job, but hopefully there are people which are working on this to do computer-aided proofs. So there are libraries, and even if it's quite challenging, but it's possible to do it even in non-trivial system. So, and let me say that, for example, now I show some example, and what I will do is also to compute the Lyapunov exponent, which is the first thing you can compute. And of course, to know the Lyapunov exponent, you have to know the invariant measure. If you know the invariant measure up to a small L1 error, you can get it from this. Well, first example is Lorentz one-dimensional map. We have seen in the seminar before this that a suitable return map of Lorentz-like flow can be quotiented. This map has a preserving foliation, so you can study it by a one-dimensional map, and which tells how the leaves are sent to each other. And this is an these maps are piecewise expanding, but with some point with infinite derivative. So we try to apply the algorithm to this. Of course, we change a little bit from what I was saying before, because there is an infinite derivative. I will not explain what, if you are interested, I can tell you, but it's not that difficult. You split the space into a piece where the derivative is not big, and you try to split the estimation in two parts and obtain another Lazota-York inequality, which is more complicated and less optimal, but still it can do the job. So this is an example. This is the formula. This is a plot of the invariant measure. What is more interesting is to say that with more or less 1 million of intervals, you get this error. Maybe this is a little bit frustrating because, but for the moment we know how to do this, and you need 7 iterate for the matrix related to the fourth iterate of the map. Why the fourth iterate of the map? Because if you take the starting map, is not, the derivative is not always bigger than 2 as wanted. So you take an iterate, the invariant measure will be the same, but of course the Lazota-York coefficient for the iterate will be worse, so you will pay this, but you will have the second coefficient will be worse, the first will be better. But okay, if you consider the fourth iterate, the contraction time for the zero average space is 7 in this case, and at the end we have this error. Let's now go beyond uniform hyperbolicity. Let us consider Mandeville-Pomeau-like map. Here the strategy is the same, but here you have not Lazota-York inequality. You have a system which is mixing slowly, is a power law decay of correlation, and you have no spectral gap, so you lose many things. But the strategy still can be applied because, as is done in many papers to prove that these kind of maps have a absolutely continuous invariant measure. They consider, in some paper, at least the one I know, they consider a suitable cone of function which, since you know that the invariant measure will be absolutely continuous with a density which diverge near to the origin, they consider a cone of functions which are decreasing and they go to infinite while x goes to 0, not too far, and they, by defining what is not, going to infinity not too fast. I said far, but I was thinking fast. And they prove that if you choose for a suitable choice of the notion of not too fast, and for the other constraint which is decreasing, the cone is invariant for the action of the transfer operator. And so this gives us a regularity estimation, because we know that we have an absolutely continuous invariant measure whose variation is not too fast in some sense. So we can apply something similar as before. Then you can consider again the Ulam approximation and prove some approximation inequality for the transfer operator, which will be in this time quite similar to the one for the piecewise expanding map. And so we can apply the same strategy, but here we know that the space of zero average measure when is not projected on the finite dimensional on his final dimensional version is contracting quite slow because it contracts at a power law speed. So we did at the beginning we didn't know if we were able to arrive to a small error, and at the end we are quite satisfied. You see, for this map with this exponent, which is not too far from 1, I have to say, you need 50 iterations, and then you have an error which is more or less the same as before with the same number of beans. And you can also find this is like a theorem. The above map has a Lyapunov exponent which is in this interval. This is like if everything is correct, this is a theorem, which I don't know if it can be proved in another way. This is an estimation. Sorry? Sorry, this is the graph of the map, and this is a graph of the density, which is not very nice, but of course, this is only an idea of what the density will be. It's like what is known. For the Lorentz map, you see, you have less density on. Yeah, we tried also some other example, and the shape of the density for Lorentz-like map is interesting. You also find some some local maxima, and then it goes down. There is one which looks like Batman. I am not here, but maybe if you're interested. Okay. Yeah. This is the point. When the derivative is big, the density goes down, but it depends on, it's a global thing, so it depends on the orbits.
So you have some accurate information about that. You know that the density is really small in these places. Can you improve the estimate?
You mean if I have some information like this, it can be improved? Yeah. It can improve? I don't know.
So you have a priori knowledge about that. You know that certain places density is really bad. So
But a bound from below.
yeah.
I don't know. Let us discuss later on this. We faced this question sometime, but we were able to avoid it all the time. so because it's not that trivial. Anyhow, this is for the Mandeville map. Of course, if you have another framework where everything is more regular, so you have other Lalzota-York inequalities with different norm, even with the CN norm and what you want, you can do the same thing and approximate the invariant measure up to even stronger norms. This is, well, I don't want to say much on this, but it's more or less the same thing as before, because you use, again, Alazot-York inequality, approximation inequality, and bounds on the regularity of the fixed point from the Alazot-York inequality. So let's go to another place which is beyond the uniform hyperbolicity, which is Lorentz-like systems. Something that we would like to do in the future is to really approximate the invariant measure of the real Lorentz system up to some distance. And to do this, we start to the simplest case. The one-dimensional case I already showed. Now let's go to the two-dimensional case, in the sense that we want to approximate the physical measure of, let us suppose you consider a geometric Lorentz flow, and you know that there is a return map on a certain section which satisfies certain properties. This will be a kind of piecewise hyperbolic system. So let us consider a class of piecewise hyperbolic system which we like, and try to approximate the physical measure for these systems. So we consider now, I don't know if it's the case to read and explain all the assumption, but probably you already know. We consider, let me explain it in a picture. The main feature of the system that we use are the ones I was saying before. The system will preserve a foliation, which is in this case will be made by vertical line. So it will induce a quotient map on between the leaves. And so we can, the idea is that we can get information for the one-dimensional invariant measure in the way I showed before, and then use this to approximate the two-dimensional invariant measure. What we use to approximate the two-dimensional invariant measure, what we use is that the leaves are uniformly contracted. And so then there are some technical assumptions on the regularity of the map, which must be not too wild, but these are technical and they can also be relaxed a bit. But let me say what is the main idea to arrive to an approximation of, certified approximation of the physical measure in this case. We know that there is a quotient map which is one-dimensional and that the leaves are contracted. Now we applied a point of view that recently we used with Zezé Pacifico and also with Vitor Araújo to study, for example, the decay of correlation of these maps, and even something more general, which is the idea to disintegrate. The idea is the following. We have, let me put here. You have our square and a two-dimensional system from the square to itself, which preserve the leaves. Suppose you have a measure, you disintegrate the measure into a marginal, which is on the x-axis, and on this marginal, this will be the projection of this measure on the x-axis. On this marginal, it will act the one-dimensional map. And on the leaves, you have many probability measures on the leaves on which it will act the contraction. So the contraction will send measure which maybe initially are not very near to nearer one. If you iterate enough time, your starting measure will converge to the invariant measure, which is a fractal made like this. We will see a picture later. And by the speed of contraction and the speed of decay of correlation of the base map, you can extract the speed of convergence of an initial measure to the invariant one. this is the general philosophy, but from this philosophy you can extract a statement which is made for computational purpose, and the statement says the following. Suppose you have the system with contracting leaves, I was saying before, and take two starting measure on your square, supposing that they have marginals. These are the projection on the x-axis, which are absolutely continuous, and with bounded variation, because we need to iterate on the projection. And then let us iterate the two measures with this map. What happens is that the Wasserstein distance of the nth iterate of the transfer operator can be bounded by something which depends on the rate of contraction of the leaves. Sorry, this is the same notation of the Lazotta-Yerke inequality, but here this lambda is the contraction of the leaf, to the n times the initial distance of the two marginal on the base. Why? This is not contracted, but it's okay for me because I can find a good approximation here with the algorithm before. Why this is not contracted? Because at the level of marginals you have a situation which is a transfer operator which is not well, is not contracting on L1, but is even not expanding. So for me it's okay. So the idea then will be the following. You no, these are the marginal of the initial. Then if you iterate, it will not increase. So this is why the statement works like this. So the idea is, okay, apply the above theorem with, by one of the two measures will be the invariant measure, the physical invariant measure. And the other measure will be, you take Lebesgue on each vertical leaf times the approximated measure that you can find for the one-dimensional map. So if you iterate many times, this will be small because this only sees the projection. So you find a good approximation at beginning, and so it will not change. And then the rest will be contracted by the leaf. So this result is the starting point for the computation of the two-dimensional system. There is something which is missing. What is missing? What is missing is that you cannot compute this exactly on the computer. The computer cannot implement the real Lorentz system. It can implement an approximation. So you need an estimation of the following kind. Now I take one measure, I iterate with the approximated system like 10 times. How far this is from the real iteration that I would like to approximate? This is much more technical and complicated. I wasn't decided to show it or not, but okay, let me show it. This is the statement is quite complicated. I don't want to explain it. If someone is interested, I will explain, but this is technical and is related to the way I define the finite dimensional approximation, which is here again a Ulam approximation, but with instead of, well, now we have the square and we divide by rectangles because I want to optimize on the two dimension, because on one dimension, on the two dimension we have two different things. So it's better to be free to choose the two sides. And then we have something that depends on the regularity of the one-dimensional map outside a certain neighborhood of the point where the derivative is infinite, and the coefficient of the Lazotta-Yerke inequality and the contraction. But okay, you can bound it in some way. And so if you do it, you obtain this picture. This is a picture of the invariant measure of a certain map satisfying the assumption. As you see, it looks like what it has to look. this is a zoom where we represent the the point where there is more measure and less measure with different colors. But what I cannot say now is what is the error of this picture, because computation is still going on, and maybe at the end of the week, but Isaiah maybe will have the answer. Maybe at the end of the week we will know what is the error of this computation. I have to say that to implement rigorously all the two-dimensional thing, it was a really long work, because you have much more many square to consider, and then if you want to compute the measure of the intersection of two intervals, it's easy. But if you take a rectangle, then you send it, it will be something like this, and then you intersect it with another rectangle, and then you want something that is certified. So you have to have a priori estimation on the distortion, everything, and so it was really a long work. That's why we did not finish, but but we are really to the end. If we and so we hope we will have a small error for this. So I think I can stop here. Thank you.